Good morning, everyone. Now we are going to apply what we've learned about the principles of electrical circuits. And first, we're going to look at the relationships between the ammeter readings. Now, remember yesterday with ammeter readings, we said that was all about the rate of flow. So if you think ammeter readings, think rate. If you've got a reading of 3 ampere, that means 3 coulomb of charge are traveling down that wire every single second. And then if you look at what we've done yesterday, we've said that if you have things that are in series, then the current is the same everywhere. So you'll know they're in series because they're in the same piece of wire, and immediately the current will be the same. The number of charges traveling over there per second will be the same as the number of charges traveling over there per second. And then if you look in parallel, now remember in parallel, you have a point where everything is choosing a direction, where they're splitting up. You've got the whole series current arriving there, and then a part of that current is going to the top and a part of that current is going to the bottom. So if you want to know what the series current was that arrived over there, that series current is the top plus the bottom currents. Now, when we look at the first question, you will immediately see A2 and A1 is in the same piece of wire, and that means their currents are exactly the same. And then if you continue with that path, right up to here, you will find over there that it's splitting up into 2 branches, and for the branches, we'll just add the branches together to get the total series current that arrived at that point. Moving on to number B. Well, A2 and A1 is in the same piece of wire. And then over there, you can choose between this branch and that branch. And the moment that you choose, just add the parts of the current together. So this current is measured by A4, this current is measured by A3, and adding that parts together is going to give you the total current. With number C, A1 is going to have the biggest current because the whole current is traveling in that wire. That's the series part of the current. And then over here, it's splitting up into 2 parts. So when you want to work out the total series current, you are going to add that 2 parts together. Now, how about A4 over there? Now, can you see A4 is just in the same wire as A3, which means they will have the same current. So A4 is actually a waste of time. Why put another meter in to measure the same current? Just be careful, this is not splitting up into 3 parts. It's just splitting up into 2 parts. So you just add that 2 parts. Now is the time to pause the video and quickly do number D and number E, and then come back to see if you were right. In number D, they have a voltmeter over there. Now, I'm actually looking at the ammeter readings, but they've got a voltmeter over there. Now, what do I need to remember about a voltmeter? In the video about principles, we said that a voltmeter has got an infinitely big resistance, which immediately tell you no current is flowing through that top part. So that means that that reading of A1 will be 0. If nothing can pass through that voltmeter, then there will be nothing passing through that ammeter. And remember, a voltmeter, you can always throw that wire away. It is not part of the circuit. Over there, no current will be choosing that top path. It's just too difficult to travel. Now we can see that charge traveling over here and the charge traveling over there per second is going to be exactly the same. Now we can see A5 and A2 is in series. They're in the same piece of wire. So immediately their readings are going to be the same. And then when you look at it, over there, the current can split up in a top branch and a bottom branch. And for branches, I just add the separate currents together. So that means I end up with 3 plus 4 to give me the total current that arrived over there. Now, when we look at this one, over there, you've got the whole series current. So A1 will be the biggest possible reading because you've got the whole current traveling. Current 1 arriving here is splitting up in 2 and 3. And if I add 2 and 3 together, then I'm once again going to have all the current that arrived here. They all combine in that middle spot. So if I had an ammeter at that spot, it would have read the same as A1. And then it is breaking up into two parts again. So once again, 6 plus 7 is also going to be that original one. Right, but what about number 4 down there? Number 4 is in the same piece of wire as number 3. So that means they are exactly the same. And number 6 and number 5 is in the same circuit. So they will be equal. So don't put unnecessary ammeters in there. If there's already one in that wire, you don't need another one. In question 5, we're going to focus on voltmeter readings. And with voltmeters, remember they're measuring potential difference, and that is all about energy. If you've got a reading of 4 volts, that means 4 joules of energy are required to move 1 coulomb of charge between 2 points. Now let's just quickly revise what we did yesterday. So we're looking at potential difference, and when things are in series, remember it's all about energy. V1 is measuring the energy used over there, V2 is measuring the energy used over there, and then obviously V total is measuring the whole energy used, and it will just be adding the separate voltages together. And when things are in parallel, we had to know that the total energy used at the top will be equal to the total energy used in the bottom branch, and that is also equal to the total potential difference over this whole parallel connection. Now over here, it's all about energy. So if we want to, we can look at the energies of the different parts of the circuit. Remember, the cell is giving a lot of energy to the charges. So they leave that cell with a lot of energy. Nothing can go up because nothing can pass through a voltmeter, but everything can move down, and it moves right up to there. Once again, nothing can pass through a voltmeter, so the voltmeter's over there, no current will be flowing there, everything is turning at that point. So there it's turning in, and all the charges are going through this first resistor. And the resistor resists movement, so it's taking some of that energy away. So when the charges arrive out of that resistor, they will have less energy. And when they go through the next one, they will have even less energy. Now if we look at this circuit, it's easy to see the V1 and V2 are measuring the same thing. They're measuring the same energy on this side, green, and they're measuring the same energy on that side, red. They're both measuring what you put into the circuit. So they will definitely be equal. But whatever you put in is equal to whatever you're using, and the only place that you're using is in this series connection. So number 5, that is measuring everything that you're using, will be exactly the same as V1 and V2. So you end up with V1 and V2 being the same, and that being equal to V5. But V5 is measuring everything that you use, and you use it in the 2 parts of the series circuit, so you can just add them together. With number B, you have 2 different batteries. You've got a battery over there, and you've got a battery over there of 3 cells, and 3 cells are giving a lot of energy to the charges. So when they leave that first battery, they will already have gained some energy. And when they go through the second battery, they will gain even more energy. And it's very important to understand that nothing is changing the energy over there. The current is splitting up, but only a cell can increase energy and only a resistor can decrease energy. So nothing changed with the energies of the charges traveling in that circuit. And now they go through that one, and you have the same change in energy at the top and at the bottom. So they leave over there with exactly the same energy. And now if you look at this, you will see V1 is measuring all the energy that you put into the circuit, and it is given by V2 and V3, one after the other. So the total energy given to the charges are V2 plus V3. And then V1 is everything that you put in, and obviously what you put in will be what you use. So the voltage over this whole parallel connection will be the same as V1, because V1 is everything you put in, and V over the whole parallel would have been everything that you use. So even if there's no voltmeter over there, you can just add your own if you want to, right, to remind you. And that one will have the same reading as V1 because whatever you put in, you must be using. Then you have to remember that when things are in parallel, the voltage over the top and at the bottom and over the whole parallel combination will be equal. So then we end up with
number C. If we look at the energies, you will see that V1 is measuring between green and red. It's measuring everything that we put into the circuit. And that is actually going to be exactly the same as what we use in the parallel combination. And remember, for the parallel, that will be over the whole parallel, and the top and the bottom will be the same. So you shouldn't be surprised that V1, 2, and 3 are all the same. Now is the time to pause the video and quickly do number D and E and then come back to see if you've got it right. Now, when we consider the energies in number D, the first thing I want to refer to is V4. V4 over there is measuring between that point and that point in the circuit, but the energy hasn't changed. Remember, only a cell and a resistor can change the energy. If it's over an ammeter or a switch or just a plain conductor, like in this instance, there's no change in energy. And that tells me that the reading on V4 is going to be 0 volt. Then if we consider V1, V2, and V3, you'll see they are measuring all the same energy difference. Between V1 is measuring what you put in, which will be equal to the potential difference over the whole parallel combination, which will be true for top and at the bottom. When we look at the energies in number E, you will see V1 measuring between red and green. And if you look at the circuit closely, you will see this is a parallel circuit. The whole current is traveling down that wire, and then at that point they have to choose between the top branch and the bottom branch. Now in the top branch, they're giving off their energy in one step. In the bottom branch, in the whole branch, they will be giving off the same amount of energy per coulomb, but it's doing this in two different steps. So here V2 plus V3 is giving you the bottom branch, which is equal to the total potential over the whole parallel, which is equal to what you put in. So you end up with V1 equals V2 plus V3. Remember with number F, we said if a voltmeter is giving you problems, making things look difficult, you can always remove it because no current is traveling through that voltmeter. So here, if you ignore the middle voltmeter, it's just a plain series circuit with one resistor after another. So V1 is just equal to V2 and V3 because what we put in, we must use. And then if we put V4 back, V4, when you look at the energies, you will see V4 and V3 are both measuring green energy on this side. And on that side, nothing changed the energy between the point where V4 was connected and the point where V3 was connected to the circuit. They are measuring the same energy on this side, and they're also measuring the same energy on the other side. So they're measuring the same difference in energy. So V4 is going to be equal to V3. When we look at number G, here you will see we've got a parallel branch with a top branch over there, that whole branch, and the whole bottom branch. And we immediately know the potential difference over the whole top branch will be equal to the potential difference over the whole bottom branch. And that means we can add the two in the top branch together because they're in series. And that will give the same as the bottom added together. In circuit H, V5 is new. V5 is actually catching you before you go into either of the parallel branches and afterwards. So V5 is measuring over the whole parallel connection, And remember, over the whole parallel is equal to the potential difference over the top, which is equal to the potential difference over the bottom. And then that gives you V5 is equal to V1 plus V2 in the top branch and V3 plus V4 in the bottom branch. To see if you understand this, pause the video, do number A and B, and then just come back to check if you're right. Now, obviously here we have the same thing. The potential difference over the top branch over there is equal to the potential difference over the bottom branch. And then we can say it means that 3 volts over there plus the 4 volts used over there is equal to the 2 volts plus whatever is used in V4. And then you just solve for V4, and that means 5 volts has to be used over there. In number B, we have 12 volts over our cells. So the cells are giving you 12 volts, and that must be used in this parallel combination. So the potential difference over the whole parallel will be 12, but that is always equal to the potential difference in the top branch and the potential difference in the bottom branch.